Hello, it's Keith here, and this is lesson 10 of the so-called ChibiFighter series, in which we look at this little tech demo I've written. It's a sort of parody of Street Fighter 2, and you can see we've got two characters on the screen, and we can make them move towards each other and fight each other. Now, this is the Sam Coupe version. Unfortunately, it is quite a bit slower than the Amstrad CPC version that it was based on, and the reason for this is basically because of the extra colour data. This is a 16 colour system rather than the 4 colour system, and what I've decided to do in this version of the game is I'm still using 4 colour graphics for the bitmap data, and then I'm converting them to 16 colours in real time, and unfortunately this is a little bit slower, in addition to the extra sheer amount of byte data having to be transferred to the screen. But we're going to look at this today because I think it's an interesting example of what we can do with regards to the Sam Coupe. We're going to be looking at how the graphics routines work and also how the sound routines work. Now, I guess the best thing I could do to try and speed the game up beyond what I've done so far would be to use a lookup table and pre-convert all of the possible byte data to screen data in advance, and that would hopefully speed things up a little bit. But as I say, this is the current state of the game and the graphics engine that we've got today. So let's go over to the code and let's take a look at it. Now, this is the start of the program. Now, the program actually loads in on the Sam Coupe a memory address 8000, but you'll notice I've got an org of 0 here. Now, why is that? Well, we're actually going to relocate the entire program. The first thing we're doing here is we are paging in the bank into the low memory area, and what we're doing is we're paging in the bank that is actually in the high memory area, so both the 8000 onwards range and the 0 range onwards contain the same data now. And the reason we're doing this is we're going to page in a different bank into the 8000 range, and that is going to be our screen memory, and the 0 to 87 FFF range is going to be our program. The reason we're doing this is we want the 0 range area so that we can use an interrupt mode 1, and to do that we've got to write a jump to the memory address 38 in hexadecimal there. So we're writing a jump here to that address, and we can't do that if there's ROM in that area. So that's why we're doing that. The Sam Coupe basic loader will load in at memory address 8000, and they say the easiest solution to that is just to page the same bank into the 0 range, and so that's what we've done. So we've paged the bank in there, and then we've got a jump to start here at memory address 100. And so basically this jump here is literally a jump to memory address 100, and because we've paged the bank that was at 8000, we would actually be running at 8000 here, not 0, but because there's no absolute commands here, it doesn't matter. So by the time we're at the absolute address start here, we are actually jumping to memory address 100, and this bank is at that memory address, so everything will work correctly. We're then paging in a different video RAM bank for the top memory range, a different 32K bank here, and we're paging that in as the visible screen. Now, this graphics engine is known as MinTile, minimum tile. This is a simple, crude graphics engine that is designed for systems that don't have a screen buffer. So that's the only memory that is paged into that range throughout the entire game. So there's never any bank switching or anything. That's a requirement of the design of this graphics engine, this MinTile graphics engine, because some systems don't have enough memory for a double buffer, and also depending on the pattern data, your game may not make it convenient to have a double buffer. So that was a design choice with this routine. So what we're doing here is we're installing an interrupt handler. We're putting a jump in at memory address 38, which is the jump address for the interrupts of interrupt mode 1, and we're then running the initialization routine of Chibi Sound Pro. Now, this is a sound driver I've written for all of my systems that I cover. We've covered that in a different tutorial, and the init routine just sets up the sound hardware to play sound, which will be played during the interrupt handler, which we'll actually take a look at right now. So the interrupt handler basically is very straightforward on the Sam Coupe. All we need to do is make sure that the banking is correct, because I would say if there was problems with regards to the sound being in a different bank to the game code, or the interrupt handler might not be available at all times, we might have to consider using interrupt mode 2, which is a real pain. So because we've done that bank switching at the start, this is all very straightforward. Now, the ChibiTracks music player that I've written basically doesn't use shadow registers. It just uses A, F, B, C, D, E, H, L, and I, X. It does not use I, Y even. So we're using the shadow AF, but we're not using the other shadow registers because I'm using them in other parts of my code. So we're pushing those and IX onto the stack and popping them afterwards, and we're running ChibiTracks play to play the sound. So that is what we're doing there. That is going to play the sound, keep the sound playing at all times. Now, as I say, this version of the Mintile engine uses 4-color graphics. I have another version that uses 16 colors, which we're going to look in the Mintile tutorials, which I think actually was a little bit faster because of not having that extra conversion stage. But this version, as I say, is using 4-color graphics. That was something that was made as a choice with this game, and there are 2 reasons for that. Firstly, the game was very much designed around 4 colors. It was designed on the Amstrad CPC, so while it could be run in 16 colors, it wasn't much of a benefit. The other thing was, I thought it would be interesting to experiment with this idea of using 4 colors, because on these 8-bit systems, using 16-color graphics becomes a very memory-intensive problem when it comes to storing all of the pattern data. A 4-color 8x8 pixel tile will use just 16 bytes, but a 16-color one will use 32 bytes. So you're doubling the amount of memory space that your tiles will use, and this can cause a lot of problems with regards to, it very quickly pushes you into having to use bank switching and also having to load in multiple banks from disk and things. And so by limiting myself to 4 colors on all systems, it meant that I was reasonably confident that if the game fit on the Amstrad CPC without any kind of bank switching, it would also run on the Sam Coupe without any kind of bank switching, which made porting the game a lot easier. Now, basically, when we're going to just look at the Mintile routines here, we've got a get screen pause routine here, which calculates the X and Y destination for the video RAM here. And then we have this routine called do strip, and this is the one with do strip reverse that does all the work of drawing the tile map and the sprite graphics. The sprites are actually miniature tile maps themselves, so everything is done with the tile map routines. The do strip routine will draw one horizontal strip across the screen from left to right in normal order. There's a do strip reverse which goes the other way for when the sprites are horizontally flipped. This version, Mintile, can't vertically flip the sprites, and it can't really do anything else. I am working on a new tile map engine which is based on this one with a lot of improvements that can do those kind of things better. So this example is at a really intermediary stage to experiment with software tile maps and hardware tile maps. It took a lot of work to port this to so many systems and get it working on all of them. I didn't feel confident enough to make something more advanced that could do vertical flipping as well at this time, and for this game, the fighting game, it didn't need it. So there was a combination of things. The game and the tile engine were designed around each other's requirements and capabilities, so that's why this system works like that. So when this is executed, basically the BC shadow registers will be pointing to the tile map data. That is a 1 byte per tile map. The DE registers will point to the bitmap pattern data, so that is our 4 color patterns for the numbered tiles. The IYL will point to the width of the tile map, and then HL will be the video destination, the VRAM destination, so that will be from 8000 onwards, and that will be either 8000 if we are just drawing the entire tile map, or it will be some offset calculated by the get screen pause routine. And so what this routine will do is it will go across drawing the tiles to the screen. Now we're loading in a tile from BC here, and the first thing we're doing is we're checking if it's 0. Now 0 tiles are empty, and these can be used either for transparency. Some of our characters have tiles that have no data in them, and so rather than being a square block, there is sort of corners that are cut out there of the graphic. We can use it for that. Mintile also uses a cache to mark what needs to be updated with regards to the background. If a character has moved, the background needs to be redrawn and things, and so the cache is used for that, and an entry of 0 in the cache is a tile that doesn't need anything doing to it. So in that case, we're skipping to empty tile, and all empty tile does, if we get to it here, is we are incrementing BC, that is moving to the next tile, and then we're incrementing our VRAM destination by 4 bytes, moving us 8 pixels across the screen, which is the position for the next tile to be drawn. So that's what we're doing there. So that's what happens if there's no tile, but in most cases we would hope there will be a tile to draw. And so what we're going to do then is, first of all, we're going to set the tile to 0, because as I say, if we're working with a cache, we would be zeroing them as we're drawing them so that they aren't drawn again next time unless they're needed, in which case the cache would be updated again. You'll notice there's some self-modifying code though, because when we're drawing sprites to the screen, those tile maps are not modified. They will be the same every time and they're drawn every time. So in that case, we would modify this to a no-up, but in this case, what you can see here is clearing the tile back to a 0. Then what we're going to do is we're going to calculate the pattern data address. That's the source pattern data that we want to transfer to the screen. So we're effectively multiplying the value we loaded in from BC by 16 here and then adding it to DE, and that is now our bitmap source. We're then transferring that to H and L, and we're going to pop it back here in this case. Now what we're going to do next is we're going to have a loop of 8 lines, and then we've got some unwrapped code here to draw one entire line to the screen to save as much time as we can. Now, as I say, the source data in the pattern array is just 4 colors, but we're going to up it to 16 colors via some bit shifting, and we're going to apply a tint to the pixels as well. Now basically our graphics are 4 colors, our system 16 colors, and so what we've got is we've got 4 possible palettes that we can use, and that is known as the tint. So we're tinting the background green, and we're tinting the Chibico and the Z80 character different colors, and the title screen was a different color, and that's all done with this tint here. So what we're doing here is we are reading in a byte from our source bitmap. Now if that byte is 0, a black 4 pixel block, then we can actually write this straight to the screen without any bit shifting, because the bit shifting around wouldn't have any effect. Now when we're writing a blank to the screen, we're simply writing the B register to the VRAM destination. The B register is of course our tint that we loaded in originally, so that is effectively what we will be writing to the screen if the byte is black there. So that's what we are doing there. What we're going to do otherwise is we are going to take the byte that we've read in and store it in C. What we're going to do is we're going to shift 2 bits out of that byte, and we're going to shift them into the correct position for the first pixel. Then we're going to shift another 2 bits, and we're going to shift them into the correct position for the second pixel. Then we're going to OR in B, and B contains our tint. So that is tinting the bytes the correct color for the screen, and then we are transferring that to the screen here. We're then moving to the right by 1 byte. We've done 2 pixels now, and then what we're going to do is we're going to do the exact same thing for the next 2 pixels, pixels 3 and 4 here. We've then done all 4 pixels that were contained in that 4 color source byte. So what we're going to do is we're going to load in another byte, and we're going to do the whole thing again. So that's what we're doing here. Basically we are unwrapping the 4 color data, converting it to 16 colors, applying the tint, and then writing it to the screen. As I say, unfortunately this is a little slower than I'd hoped originally, so I think when I do the updated version of this with an improved tile map code, I'm going to look at doing some kind of lookup table of the 4 to 16 color conversions. I think that's going to be appropriate on this system. So I've learned a thing that needs to be changed there. Now after we've done a line, basically we need to move down to the next line and do the same for the other 7 lines. So what we're doing here is we are adding 128, which is hexadecimal 80 there. We're subtracting 3 because we've just moved across 3 bytes anyway when we've done the pixels, drawing them to the screen, so we're subtracting 3 there. What we're doing then is we're checking if we need to increment the H part of the 16-bit VRAM destination. Once we've done that, we're decreasing our loop counter in the shadow registers there, and we're repeating until we've done. Once we're done, we need to move back up to the previous tile position. So we've gone down, drawing the 8 lines, and we jump back up, and then we move across to the next tile, go down, jump up, and move it across. And we repeat in that format. Now, in some cases, you could argue that it would be better to go entirely down the screen and move across and entirely down the screen in that kind of format. That may well be true for this system. The difficulty is that this Mintile engine that I've written here is a multi-platform engine, so it's designed to do the same job on every system, even though some of those systems work in very different ways, and so some of the systems just have to kind of suck it up and not have ideal structures for the code. Rewriting the entire engine for every system to work in the optimal way for that system wouldn't be possible really or practical. Some systems benefit, like some systems work down the screen and some then across, like the BBC and things, and others don't, like this one. So as I say, it's a case of making the best of the way that the code works that I could on each system. So that's we're now in the position for the next tile, so we're now decreasing the tile count here and seeing if there's any more tiles for this line. Once we've done that, we are then basically clearing bit 7 of the L register here, and we're returning, and this is getting us ready for the next line of the tile map. So when we return, we will pass to a calling routine, which will be drawing an entire screen of lines or a sprite of lines maybe, and it will move down the screen as required. And so we're just updating the HL pair there so that that will work correctly there. Now we've got the do strip reverse version. This will go from the right and move left, filling the tiles in that direction. But basically we've got the same kind of code. We're loading a tile number in from the source tile map. We're calculating the pattern source data, which of course is not flipped. And then what we're doing is basically the same again. We're loading in a byte of 4 pixels. We are then storing that in C. We've got our blank drawing routines again, and we're just bit shifting the bits in different orientations here to get the bits in the opposite pixel order for the screen. And this is ironically one of the things that it's kind of easier to do on the Sam Coupe than some systems, because as I say, when you've got only 2 pixels in a byte, swapping them over is not so obscure as compared to a system like the Amstrad CPC, where you've got 4 pixels in a byte and the bits are kind of all over the place, which is why I use a lookup table on that system. I think ironically for this system, rather than using a lookup table necessarily for flipping the graphics, I think the more important thing to do would be to use a lookup table for converting from 4 to 16 colors, although if I had enough memory I would probably use lookup tables for both, and that is something I will be investigating for the next version of the improved graphics engine that I will be working on. So there we go. So if you've liked what you've seen, please like and subscribe. As I say, I am working on an improved graphics engine for this kind of software tile map functionality, which is going to support horizontal vertical flipping, speed filling, sprite, double height sprite scaling, and a few other tricks and things, and there will be various speed improvements and corrections to limitations of this engine. So as I say, though, you can go to the website and download the source code, the build script for today's example, and you're welcome to use it in any of your own projects, in anything you can, as I say. Even if they're commercial, you don't need to give me credit. It's educational stuff. I'm hoping you'll get some interest and some learning out of it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.